their diameter or their size. And then we center them, these agglomerates, I will show you how it works, and then after centering they get crystalline, they become very spherical, and then they finally take them inside a deposition chamber where you have a sensor device and you deposit these particles just like a billiard bar, they keep on getting and deposited onto this electrode structure. And you can, depending on how much you want to deposit, you can control that and you can deposit. You can make a sensing device. So the sensing device is kept there inside. So I just want to quickly go through what is the kind of structure you have. So I will show you the transmission electron microscopy picture of what you have here, and as the nanoparticle goes through this journey, what happens to its size and shape, and then you will understand how we are able to control the size of these nanoparticles. So this is what in fact is very important, that if we don't have any control, this would be the size distribution of the particle. You can understand that although we will say that I have particles of this size, but I will have a very broad size distribution, and that's not good from material science point of view. What we are doing is, from this broad selection, from broad distribution of the particles, we are selecting particles which are this very narrow size distribution. So we can select particles of this size. If we want to select particles, let's say of this size, we have to shift this distribution in that direction so that this peak comes at that point where you want to select. So there's a lot of manipulation of the material has to be done. And in the next step, what you can say that this is what you prepare in the beginning. And as you are centering this agglomerate, you can see that this is in fact a magnified picture. This agglomerate, you center it, you see it from the contact particle. You center it more, it forms this kind of particle. And finally, when you center it at appropriate temperature, each of this agglomerate is getting converted to a spherical particle. You can see that all particles are exactly of the same size, very narrow. Exactly is not, it's a wrong, technically wrong word, because there will always be very small distribution. But the distribution is very, very small. Okay? And that's what we have been able to achieve this. And you can see that by changing the voltage in the differential voltage analyzer, you can select particles of different diameter. 6.5, 11.9, 15.2 nanometer. Very accurate control of the size and size distribution. If you look at one of them in the high resolution transmission electron microscopic picture, what you're seeing is these lines are nothing, but these are the atoms sitting atomic lines, atomic planes. You can see that these particles are not only spherical, the size is controlled and they're completely crystalline. They don't have any defects or anything. So this is the method which we are using to prepare different types of metal and metal nanoparticles. This is how this looks like in the laboratory. If any of you are interested, this is available in block 6 and you can demonstrate this. We have used this for the last 10-15 years. We have been working on development of this technique. And we have used this technique to prepare palladium, which I'm going to discuss today. That's the first material we prepared for hydrogen sensing. And then we modify this palladium property by aligning it with palladium, copper, and radium silver. That's to modify its interaction with hydrogen, so that you can improve the sensitivity and selectivity. Then for some other application, we are preparing silicon and silicon tin alloy nanoparticles. That's not for sensing purpose. We can also prepare core shell nanoparticles, where the core of the particle is palladium and it's capped by a carbon shell. This is to protect the surface of the particle from unwanted reaction which can take place. Your sensing gas should go through this carbon shell and react at the surface, and unwanted molecules can be the particle has to react. Similarly, we are able to prepare tin oxide, indium oxide, and zinc oxide nanoparticles using this method. And so let's move to the first example, palladium. In fact, initially we did this work as a part of a project which was funded by Marie Curie Action. It was in collaboration with the university in Germany, and the European Commission selected this project as one. They selected 75 projects, and this was one of the successful projects. So it's very satisfying. But since then, we have now expanded this, and we are using this method to prepare different types of nanoparticles. Quickly, I will show you. This is a typical resistive sensor. Now I am showing you the actual sensor, how it does it work. So you can see that this is the electrical resistance of palladium when exposed to air. When the moment you expose it to hydrogen, the electrical resistance increases and it gets saturated. on that. This change in the electrical resistance is what is your sensing signal. Okay, so this AC value of sensitivity, although it's already mentioned, is susceptible to noise and drift, and the sensor keeps on going up and up, or sometimes keeps on going forward. So this was one of the. So this is not a palladium nanoparticle. This is a palladium bulk material. You take a wire of palladium or a thin film of palladium to do it. This is what is normally used on an industrial scale for sensing hydrogen. Okay, and this process takes place at close to 3 to 4% because you know that that's the explosive limit for hydrogen. And what we do is we do the palladium nanoparticle sensor. We see that now the complete sensing response has got modified. From the slow saturation response, you can see it, sorry. You see it here. The sensing response was just increase in the resistance on exposure to hydrogen gas. And what we are showing now is the moment you expose it to hydrogen gas, there is an increase in the resistance and automatically it comes down. The sensor is still exposed to the hydrogen gas. So what you get is a pulse-like response. The response is not now DC. It is just increase in the resistance and then decrease in the resistance. When you remove hydrogen gas, again there is an increase in the resistance and there is a decrease in the resistance. This complete modification of the mechanism has taken place when we have gone from palladium bulk, palladium wire or thin film to palladium nanoparticle. And we now understand because there are two processes which are taking place. These we call them a geometrical and electronic effect. Why is there a change in the electrical resistance of palladium when exposed to gas? Hydrogen atoms goes into the palladium structure. They start scattering electrons. They are defects and they become scattering center in physics we call it. Scattering center for electron. And so resistance of the material increases. That's the typical. But in addition to that, what happens is when hydrogen gas goes into the palladium gets expanded by 4 to 5%. So in case of the palladium bulk or palladium wire, this is the big problem because the sensor, once it goes to 100 and 200 or 300 cycles of expansion, contraction, it breaks down. A palladium wire becomes powder of palladium after some time, and that's what restricts the life of the sensor. What we have shown here is when you have palladium nanoparticles, there is some gap between the palladium nanoparticle. So the resistance is initially high, but when the gas comes, the particle expand, the nanoparticles start touching each other, their electrical resistance comes down. So the initial resistance increases due to electronic effect of hydrogen acting like scattering center and decreases due to geometrical effect. And now we understand that this is two effects and we can mathematically derive their response time and their sensitivity. And now we can see that we can understand as a function of the size that here I'm showing as a constellation, you can see the geometrical effect, its magnitude is very high. Sensitivity is very high, but the response time is slow. It takes a long time. Electronic effect, the sensitivity is low, but the response is very fast. So this combination of geometric and electronic, it is giving us higher sensitivity, better response. So it is some sort of a synergic combination of geometric. In addition, the nanoparticle, there is a volume for expansion and contraction, and that makes them more stable and they can stay on for a long time. They are not susceptible to degradation. So I will quickly go to the second type. So what we know, we saw different types of sensors. So in this case, what we are doing is we are not even using palladium particles. This gives you an example here that this is the sensor which we have now. This sensor is, you can see that this is a base, but on that you see there is a carbon layer kind of construction, and this represents graphene. So there is a graphene layer. On the graphene layer, we have deposited some palladium particles. You can see the palladium particles are not even touching each other. Normally, if the graphene layer was not there, there will not be any response because there is no electrical connection. What we have seen here is that if the palladium thickness is very large, of course you will have sensing due to palladium which I discussed. And that is very bad because this palladium breaks down after some time. And what we want to get rid of that problem that we now have isolated particles of palladium. When hydrogen comes, it reacts with this palladium it changes the properties of the palladium to palladium hydride when it forms. So the electrical interface between palladium and graphene gets modified. And there is an electrical change because of the electrical changes which are taking place at the interface. This is what describes the electrical phenomena. It's related. You can see that this is graphene conduction band, and this is palladium. In graphene palladium, the electron shifts from graphene to palladium because of the electrical properties. So you have this positive layer is formed. When you expose it to hydrogen, electrons go back from palladium hydride to graphene. And you can see that this change in the positive charge at the graphene layer, there is change in the electric property. The beauty of this process is that you don't have a continuous layer of palladium. You have very isolated palladium nanoparticles, and they are not even touching each other. So there is no question of the instability after a lot of cycling. The changes are only taking place at the interface, and this is a very fast response. The response becomes very fast. So this is the method which we in fact were choosing. I will skip this. So now we go on to the next stage. What we are saying is this sensor now has two types of particles, and they are all isolated. So you have some of them are palladium particles, and some of them are tin oxide particles. So in case of palladium particles, you can see that when we have only palladium, the sensing is due to graphene palladium interface. When you have tin oxide, the sensing is due to graphene tin oxide interface. You have two types of sensors. This will work for two different gases. The same sensor will give you different response for two different sensors. Just to give you an idea, so you can see that this is a sensor, so these are different colors. This is a palladium sensor, this is a tin oxide graphene sensor, this is a tin oxide palladium graphene sensor. You can see that palladium sensor, as you increase the temperature, its sensitivity decreases, whereas tin oxide palladium sensor, as you increase the temperature, the sensitivity increases. Both types of sensors are behaving in different ways. The proposal is that you prepare this kind of sensor. Sensor will be based on tin oxide, indium oxide, and zinc oxide particles deposited on graphene. Tin oxide particles are sensitive